Hello everyone, welcome to week 5 learning videos once again, and we are still in learning objective 3. So as you have seen that in the last video I showed you how to calculate risk return and variance covariance matrix to derive an efficient frontier and optimal risky portfolio. So in this video I will be using these inputs to optimally derive an efficient frontier and an optimum risky portfolio. So I use the same Excel file that I used in the last video. So this is the spreadsheet model for deriving the efficient frontier. And theoretically, you know that efficient frontier represents different portfolios, and each of the portfolio represents the highest level of return for a given level of risk for a particular feasible set of investment. In our case, we assume that our feasible set of investment is these three seven stocks. So we will derive an optimal risky portfolio and an efficient frontier based on this feasible set of investments. So first of all, what we have is annualized standard deviation and the excess return for the 7 stocks. They actually came from the last video that we have seen. You can remember we calculated the annualized standard deviation for each of these stocks in the last video. So for example, for BHP, annualized standard deviation was 0.39. So that's the annualized standard deviation for BHP, that's 0.39. And also this is the excess return, and that also comes from the last page. So this is the expected excess return for BHP, which is 0.062, and you can see this is 0.062. So I have simply copied this annualized standard deviation and expected excess returns for these 7 stocks and pasted them here. So next part is the covariance matrix, and you can see that these are the covariance for each pair of stocks. For example, this is the covariance between BHP, and you know that when we calculate covariance for the same stock, it's basically a variance. But this one is the covariance for BHP and Foster's Group. These are the covariance for BHP and Fairfax. They also come from the previous calculation. So you can remember this is the variance covariance matrix for the 7 stocks that we have. For example, this the Foster's Group and BHP's variance covariance is 0.024, and you can see that's the BHP and Foster's Group covariance is 0.024. So each of this number is representing the covariance between each pair of stocks. And I simply have filled up the other part of the covariance matrix, and you can remember that, that this other part of the covariance matrix is simply the mirror image of the top part. Then if you look at this extreme left column, this is basically the weight of individual stock in our portfolio. And initially we have an equally weighted portfolio. So since we have 7 stocks, so each stock will have a weight of 1/7, 1/7, 1/7. And I have just copied these weight in along this line. Okay. And then this is the sum of these weights, and you know that sum of these weights must be 1 all the time. And here what we have is we have the variance of each of these stock considering the weight. So you can see that C6, that's the weight of this stock and the sum product of the weights and the weights of the other stocks. So this is the variance of the portfolio, and the same way we calculate all of them. And then if we look at this mean excess return, mean return, now first of all is the mean excess return. You can remember we have the excess return for the 7 stocks here. So mean excess return should be the multiplication of individual return with the corresponding weight. So we have used the sum product function. A18 to A24 is the weights for each of these stocks, and then D6 to D12 are the excess return for each of these stocks. So this is the sum product of the weights and the excess return. And this is mean. So what we have simply did here is the mean excess return is added by the risk-free rate. So that is the mean return. And that's the standard deviation. So calculate this standard deviation, we have simply summed them, and then we got the square root because this is the variance. So we got the square root to get the standard deviation. And first of all, slope, last of all, slope, you can remember the slope is the excess return divided by the standard deviation. So we already have excess return, that's for example 0.370, and then we divide it by the standard deviation. That's the slope, or the you can say the Sharpe ratio. So now we have all the inputs to go for optimal risky portfolio and efficient front end. So we prepare a table like this before we go to calculate our optimal risky portfolio and efficient front end. So first of all, you can remember from our previous discussion that our efficient front end starts with our minimum variance portfolio, then it moves along the other possible combination of the portfolios, and it moves along the optimal risky portfolio. So we will start with our minimum variance portfolio. So to get this minimum variance portfolio, we need to use an Excel add-in, that is a solver. So we go to data, and we have to have this Excel add-in solver. If it is not added in your Excel, you can add in it in the same way as we added our data analysis add-in. So we go to File, Options, Add-in, Go, and we click this box, solver add-in. We click OK, so we get this solver. Now we open the solver. What the solver is basically an optimizer. So what we will do, we will set an objective, and we will seek to achieve this objective by changing composition of some other numbers. So I delete all the numbers first of all, so that it becomes easier for you to understand how we set all of them. So first of all, we need to set our objective. You know, our objective will be to minimize our standard deviation because we are after the minimum variance portfolio. So A28 has to be minimum. Okay. Then how we can want to achieve these objective? We want to achieve this objective by changing these numbers, because these numbers are the weights, and by just manipulating this weight we want to achieve our minimum variance portfolio. And then we add one constraint here, that this one has to be equal to 1, because you know that sum has to be 1. So now we have all the objectives and the constraints set in. So we go for solve. Okay. So if you carefully look, we previously had different weights. Now the weights have been changed. So we copy these weights and paste them here. Okay. Along, we also copy this mean, standard deviation, and slope, and we paste them here. Okay. So we got our minimum variance portfolio. Now we will get the optimal risky portfolio in the same manner. Now our objective is different, because our objective is not to get the minimum standard deviation. Our objective now is to get the maximum Sharpe ratio. So this A29 maximum. All others remains the same. Okay. So you select solve. Okay. And our weights have again been changed. So we copy these weights, paste them here. We also copy the mean, standard deviation, slope in the same way, and we paste them here. Okay, so now we got the two most important points in our efficient frontier. The starting point, that means minimum variance portfolio, and the optimum risky portfolio, that is supposed to be the tangency of the efficient frontier with the capital allocation line. But the next step is we need to get some other points in the efficient frontier, because you know that we cannot have only 2 points in the efficient frontier, that's the minimum variance and the optimal risky portfolio. We need to have some other points. So we need to have some other arbitrary mean values. Okay, that's a little bit of tricky because we need to set these mean values arbitrarily in a way that we have a smooth shaped efficient frontier. So since this is our starting point, 0.0781, and this is the optimal risky portfolio, so this is 0.0939. So I will get some points in between, and here there will be some points beyond this. So let's put some numbers, for example, 0.088, 0.0833, 0.0867, and then 0.0900. And here we get 0.0950, 0.100, and 0.1050. Okay, so these are some arbitrary numbers. You can use other numbers as well, but you need to make sure that these numbers are consistent with the 2 points that we already obtained. So now we will get the weights for all these mean values again. So I'm sorry, it's 0.1050. So we got to solver again, and all others remain the same. We have the same objective. We have the same constraint here that these are the weightings we will be changing, and the sum of the weights must be 1. But we have to add another constraint, because now what we want is that the mean that we have here must be equal to that one, because that's the arbitrary mean value we have set. So we add this constraint here, and then we solve for. Okay, so similarly we copy the weights and paste them, and also we copy them and paste them here. So now we get these numbers in the same manner. So I am doing it very quickly. So every time we need to change this, and we need to get the weights. And that once again, I change this one. I understand that this process is a little bit cumbersome and lengthy, as we have to solve and copy paste every time, but for now that's the best option available for us. So now we have got all the points in between the minimum variance and the optimum risky portfolio. And now we will obtain the points beyond this optimum risky portfolio. So we go to solver again, we change it. Once again, the last point. Okay, so we are done with all the points that we need to develop an efficient front end. So we have the mean, standard deviation, and the Sharpe ratio. And now if we look at the efficient front end that has already been developed, and you can see that we have a nice smooth shaped efficient front end. So this is how we basically develop our minimum variance portfolio, which is this, and optimum risky portfolio, and derive the efficient front end. So that's the end of this video. Please watch the next video to see a discussion on how we actually draw this efficient front end.